Welcome back, everyone. Apologia, 8th grade physical science, week 12, day 4, textbook pages 196 to 200, notebook pages 157 to 160. Graphing speed. I said that when you bike, you likely do not travel at a constant speed. But think about a car on cruise control that is set at 55 miles per hour. The car travels the same distance in the same time frames because the cruise control determines that the car will travel 55 miles every hour it is moving. That is constant speed. Constant speed means equal distances are covered in equal times. Suppose you decide to jog around a marked track at a constant speed for a half an hour. How could you check that your speed is constant? You could use a stopwatch to time how long it takes you to jog a lap of the track. If you jog each lap in the same amount of time, then you are jogging at a constant speed. Let's say that you jogged 3 laps, and each lap, 400 meters, took you 2 minutes. The next day, you want to go back to the track, but you only have half an hour before you need to head home. You'd like to jog 14 laps. Can you jog 14 laps in half an hour? How can you figure that out? You can calculate the answer using equation 6.1 and rearranging the equation for time. So time equals distance divided by speed or velocity. But another way to find out the answer is to make a distance-time graph. A distance-time graph is a good way to describe motion. Look at the graph in figure 6.9. This is a graph showing the 3 laps you jogged. Notice that the distance is marked off on the vertical y-axis in units of laps. Here we go, the distance in laps. So 1 lap, 2 laps, 3 laps, 4 laps, and so on. We could also use units of 400 meters, but we'll use laps since the numbers are smaller. Time is marked off along the horizontal or the x-axis in units of minutes. So we have 5 minutes, 10 minutes, 15 minutes, and so on. Notice the 4 points on the graph. There is a point at 0 time right here and 0 distance. At 0 time, you had not yet jogged any distance. The point at the time, 2 minutes, is placed at 1 lap to show that it took 2 minutes to jog the first lap. So here's the first lap, and we go over and you can see the dot here is at 2 minutes. There is another point 2 minutes later showing another lap was jogged. So we go up to 2 laps, and then we go over, and it's at 4 minutes. Again, a point is placed 2 minutes later at 3 laps. So you can see on the graph that after a total time of 6 minutes, 3 laps were jogged. So we have 6 minutes, and if we go up to the dot and then across, we can see that we were at 3 laps. You can draw a straight line through all 4 points and then extend the straight line to 30 minutes. So if we had a ruler, we would draw a straight line and we'd extend it to the full 30 minutes. The solid line indicates the actual times and distances you ran. The dashed line is called an extrapolation, like you did in experiment 1.2. Remember, an extrapolation is used to estimate values that are either higher or lower than the actual data collected. Now that you have the extrapolated line, you can see how long it will take you to jog 14 laps. Follow the red line to the right from 14 laps on the y-axis to the blue extrapolated line. Then follow the red line down to the time axis. It will take 28 minutes to jog 14 laps. All right, so here we go. 14 laps. And if we want to figure out exactly how long it will take, it'll take 28 minutes. Now that was a pretty easy example, but I wanted you to see how to use graphing to describe motion. Let's consider another example. Suppose you're jogging with a couple of friends. One friend can't keep up with you. You find that they take 2.5 minutes to jog each lap. Your other friend is faster than you and can jog a lap in 1.5 minutes. The graph in figure 610 shows a distance time graph describing the motion of all three joggers. All right, so the blue line, this top line, the blue line indicates your faster friend. The red line, the middle line, is me, the jogger. And the gold line indicates your slower friend, the bottom one. What can you say about the steepness of each line? The faster jogger has the steepest line. They covered more distance in the same amount of time as you. The line describing the motion of your slower friend is not as steep as yours. They covered less distance in the same time. Their speed was slower. So we have the steepest line, the fastest jogger. The less steep line is the slowest jogger. You can compare constant speeds on a distance time graph. The greater the speed, the steeper the line. The steepness a graph line is called the slope. The slope of a line on a distance time graph is speed. A steeper line has a steeper slope. Thus, the greater the slope is on a distance time graph, the greater the speed. What if the average speed isn't constant? How will that look on a distance time graph? Well, constant speed is shown by a straight line. Changing speed is shown by a curved line. Look at this graph on figure 611. It is showing the speed of a car. Okay. The slope shows straight lines from 0 to 40 seconds. From 50 to 70 seconds, and from 80 to 100 seconds. These are the times that the car displays constant average speed. From the graph, we can see that the car travels 240 meters in 40 seconds. So in this 40 seconds, we can see that we've traveled 240 meters. Using equation 6.1, we can find the speed of section A. So the speed is distance over time. So 240 meters over 40 seconds is 6 meters per second. What is the car doing during section B of the graph? This section. From 50 to 70 seconds, the car stays at 300 meters. It hasn't gone anywhere. This means the car is not moving, so we can say it has a constant speed of 0 meters per second. The car didn't move. A flat horizontal line on a distance time graph means the object is at rest with a constant speed at 0. So this line right here just tells us constant speed at rest of 0 meters per second. At 70 seconds, the car starts back up and moves again until we reach section C, 80 to 100 seconds. Let's figure out the speed of the car during that time interval. So the speed is the distance over time. So 340 meters over 20 seconds equals 17 meters per second. The car is moving faster during the last 20 seconds of the graph than it is during section A. So it's moving faster here than it is here. We can see that with our numbers. It's moving at 17 meters per second here. It has a steeper slope. And here, it's moving at 6 meters per second. The sections of the graph that are circled are the areas where the car is changing speed. The circle between A and B shows the car gradually slowing to a stop. Here, this kind of a curve here. It's slowing down. So the line has a slight overhand curve. The circle between B and C shows a slight underhand curve, which indicates the car is gradually increasing speed here. So it's speeding up.